Hey guys, let's do this problem right here. The question is asking find eigenvalues, find eigenvectors, find the basis and the dimension of all eigenspaces, find algebraic and geometric multiplicities, and determine if A is diagnosable, find matrices P and D such that P inverse A P is equal to D, find A100. Let's see how we can do these things. So first let's begin with the eigenvalues. So to find the eigenvalues, there's a general equation that's determinant of A minus lambda I is equal to 0, and from this one we can find the eigenvalues. So let's see how we can do this. So determinant, so A minus lambda I, so I mean basically identity mean, it's going to be 1 0 0 1 1 0, because we are taking 2 by 2, so it's going to be 1 0 0 1. And if you multiply the lambda by lambda by 1 0 0 1, you will get something like this. So 1 0 0 1, and if you multiply the lambda, it's going to be lambda 0 0 lambda, right? And if you substitute this is the A, and if you substitute, you will get 2 minus lambda 3 over 3 2 minus lambda, so like this, and that is equal to 0. And now what we have to do is we have to calculate this determinant. To calculate this, we have to use AD minus BC. So AD minus BC AD is going to be simply multiplication of these two, so it's going to be 2 minus lambda square, and BC is going to be simply this multiplication, so it's going to be minus 9, and if you expand this one, it's going to be 4 minus 4 lambda plus lambda square minus 9. And let's bring it all together, and it's going to be lambda square minus 4 lambda minus 5 is equal to 0. And we can factor this one now. So if I when I multiply, I have to get negative 5, and when I add, I have to get negative 4. So it's going to be negative negative 5 plus 1. So negative 5 plus 1. So if I take that, it's going to be lambda minus 5, lambda plus 1 is equal to 0, and therefore lambda is going to be equal to 5, and lambda is going to be equal to minus 1. So this is the answer for the first question. These are the eigenvalues. The second question is asking find the eigenvectors. So let's see how we can do this. So to find the eigenvectors, we have to simply do the null space. So if I do the null space, for example, it's going to be A minus lambda I is going to be 0. This is the basic null space, right? So in this case, what I'm going to do is first I'm going to begin with the lambda is equal to 5. So we have to do for both of them. So first of all, I begin with the lambda is equal to 5. If I do that, I simply substitute lambda for this lambda for this lambda 5 for this lambda. So it's going to be 2 minus 5, 3, 3, 2 minus 5, and that's going to be equal to 0. So we set that's one equal to 0 and solve this one. So it's going to be minus 3, 3, 3, minus 3. Then if you do the Gauss Jordan, you will this bottom will be eliminated, and you can simplify the top one by dividing by 3. So it's going to become minus. It's going to become 1 minus 1 0. So it's going to be 1 minus 1 0 0. So this is what you will get when you do the Gauss Jordan. Therefore you can say x minus y is equal to 0, therefore x is equal to y. So that's the answer for the first one. So we know this is free variable because this doesn't have pivot. So this is our free variable, so we have to write everything in terms of free variables. Therefore the answer is going to be y comma y, but we have to write it as, so eigen vector for lambda is equal to 5, are y comma y, and I have to take y common, it's going to be 1 comma 1. We can also write this one as span of 1 comma 1. So this is the final answer for this one, when lambda is equal to 5. But we have to find the lambda is equal to minus 1 too. So if I find that one, it's going to be, for lambda is equal to minus 1, minus 1 is going to be, I substitute minus 1 for this lambda, so it's going to be 2 minus minus 1, so it's going to be 2 plus 1. Then here it's going to be 3, 3, 2 plus 1. In this case we will get 3, 3, 3, 3, and if you do the Gaussian run, you will get 1, 1, 0, 0, 0, 0. So this is going to be x plus y is equal to 0, therefore x is going to be equal to minus y. So we know this is our free variable, y is our free variable, so we have to, because it doesn't have pivots, right? So free variable, the column doesn't have pivots, so it's going to be free variable. Therefore x is equal to minus y, so we have to write everything in terms of free variable, so it's going to be minus y comma y, and therefore eigenvector for lambda is equal to minus 1 are minus y comma y, and we can write it as y common, so it's going to be minus 1 comma 1, and we can also write it as span of minus 1 1. So this is the answer for the second question. And the third question is asking find the basis and the dimension of the all eigenvectors. So for the C, when lambda is equal to 5, basis is going to be this same thing, right? But in this case we shouldn't write span. Basis mean when we write basis we shouldn't write span. It's just simply 1 comma 1. So that's it. And for lambda is equal to minus 1, it's going to be, basis is going to be just basis equal to minus 1 comma 1. So this is the answer for the third question, and they are also asking the dimension. Since we have only one free variable, the dimension is going to be 1. So it depends on the free variable. If you have two free variables, dimension is 2. So here it's going to be dimension is 1 for both of them. Dimension equal to 1, dimension is equal to 1 for both of them. Then the third question is asking find algebraic and geometric multiplicities. So let's see how we can do this. So I choose a different color. Okay, here we go. So this is the C question, right? The C questions are asking find out algebraic and geometric. So first of all, we have to know what is algebraic multiplication. So algebraic multiplication basically, for example, if you have lambda of minus 5 square, then it's going to be algebraic multiplication of 2. But in this case, it's just 1 square, right? It's just 1 power. It depends on the power. Like if you have 3 power, algebraic multiplication over 3, and it depends on the power. So in this case, it's just 1. Therefore, it's going to be algebraic lambda is equal to 5. So lambda is equal to 5 is going to be algebraic multiplication of this, or you can say algebraic multiplication for lambda is equal to 5 is 1. And also you can say geometric multiplicity, it depends on the dimension. So if you have dimension 1, it's just 1, geometric multiplication is just 1. So it's going to be geometric multiplication for lambda is equal 5 is just 1, and same method for the other one too. So algebraic multiplication for lambda is equal to minus 1 is 1, because if you see the lambda plus 1 is just power 1, so it's going to be just 1. And also dimension of the lambda equal to minus 1 also 1, therefore geometric multiplication for lambda is equal to minus 1 is 1. So this is the answer for the D question, and the E question is asking determine if A is diagonalizable. So it depends on, so if we have algebraic multiplication and geometric multiplication equal, it mean it's diagonalizable. So we have to check for each of them. Lambda equal to minus 1. So for example, what happens if we have 2 here? If you have 2 for example, algebraic and geometric multiplication for lambda equal minus 1 is 2 for both of them, then it doesn't matter if it's 2 and if it's 3 here, it doesn't matter if both of them have same thing. Lambda is equal to 5 has to have geometric and algebraic same number, and lambda is equal to minus 1 has to have geometric and algebraic multiplication same number. So if it has same number, it means it is diagonalizable. So that's the answer for the E question. F question is asking find matrices P and D such that P inverse AP is equal to D. So it's basically easy question. What we have to do is we just arrange the bases in a column. For example, lambda is equal to uh, lambda is equal to 5. I arrange this into column. The basis is 1 1, so I arrange this in a column. It's going to be 1 1, and lambda is equal to minus 1. I arrange this in a column. It's going to be minus 1 1. So this is going to be my P. If this is a P, then D should be 5 0 0 minus 1. It depends on the arrangement. So if you arrange the basis for 5 in the first, you have to put the 5 first. And if you in case if you switch the around, like if you put the minus 1 1 in here and 1 1 here, then you have to put the minus 1 on top right here and 5 right here. So it depends on where you put it. Both of them are right way, but we have to be careful about the side we are putting. So that's the answer for the F question. And G question is asking find the A100. So this is the equation, right? This is a general equation, but from we can find the A100 using this equation. Let's see how we can find it. So if you look at the equation, the A is multiplied by P inverse in the P, but we have D, but we have to separate this A to find the A. So how we can separate the A? We can simply multiply the P in front of them. For example, let's see. So if we multiply P in front of them and P inverse, it will cancel, and A and P, to get rid of the P, I can multiply this one by P inverse. So if I multiply this by P inverse, I will get, so in the I have to do the same thing in the other side. So on the other side it's going to be, so we in the other side, but we have D, so I have to multiply D by P. So it's going to be PD, and here it's going to be P inverse. Now both of them cancels each other, therefore A is going to be equal to P D P inverse. So what is it going to give us? We know the P already is 1 minus 1 1 1, and we simply substitute. So I will continue here. So we simply put that value here. So 1 minus 1 1 1, and then use multiply this one by D. D is here is 5 0 0 minus 1. But in this case, what you have to do is, since they are asking for A power 100, the question is A power 100, right? So A power 100, therefore it's going to be D power 100 we have to find. So it's going to be power 100. Then we have to multiply this one by P inverse. P inverse is going to be 1 minus 1 1 1 inverse of this, and if you calculate the value, this will give you the A power 100. So this is how we do these questions. I hope you guys like this video. See you next time.